Hello, welcome to Erudite. In this video, we're going to start exploring networks and the many ways in which they can be presented and appear to us when we're programming. Now, this is an absolutely huge topic, and to begin with, I think I'm just going to cover some basics, and then as we do projects in the future, we'll unpick and explore some more interesting and quite wacky aspects of networks. But in this video, I just wanted to show you how networks can show up in places you don't always expect, and they can look different to how we might assume they look. So that's the big takeaway from this video. So we just got this small Jupyter notebook here, and we're just importing a couple of things. We've got SymPy, Matplotlib, and NetworkX. And in fact, we're going to come back to NetworkX quite a lot because it's a really useful tool for exploring networks. And we'll just run this. While that's running, we can have a look down here at this network matrix that I've created. And this is just a simple way of showing if there's an edge connection between a node, that point on a network, if there are connections between those points. And those connections are often drawn as a line, and that line is called an edge. Well, this matrix is sometimes called an adjacency matrix. It shows where there's a connection. So if there's a 0, there's no connection. And if there's a 1, like here, there is a connection. And the way I've done this is we've got A, B, C, D, E, F, G, and H, and A, B, C, D, G, I can do the alphabet, I promise. E, F, G, and H. And so here we can see that there's an edge between A and B, because it's in the A line and the B column. But this is not very easy or clear to see. Now let's just run this. And if we present it in a nice matrix mode, we can see down here, there's our matrix. But instantly you can say, well, okay, that's one way of representing a network, but it's not very clear. And it gets very large very quickly, because for every node you have to have a line that's equal to the length of the entire network, or the number of nodes in the entire network. So this gets very large very quickly. But you can also do some things which we're not going to do here, but you can put the weight of that edge. So for example, if you had a map of cities and you wanted the distances between the cities, you wouldn't just want to say the cities are connected, you'd want to say how they're connected. So maybe the number of miles or the number of kilometers between those cities. And so you could use that as your numeric figure. So if there's a 0, then they're not connected at all, or even you could use a letter designator. And then if there's a numeric value, then that's the distance between those things. So you can use this in absolutely tons of ways. And we can represent this matrix as a grid. Let's see, there we go, like this. Now this is not quite the same though as a grid that you might see in, say, a game or in an interface. And in fact, I'll have a quick look at one of those, just pulling it up side by side. So this is just a grid representation of the matrix that we had before. And that just shows effectively a yellow block where you have a connection and a purple block where you don't have a connection. So you can more easily, quickly see where connections are forming. Now I might want to change these labels to be the labels of our nodes instead of just numeric positions, as at the minute it's just taking the index position. But if you have a grid like this, you can often see where, say, this position here, it's treated as though it's got edges to all of these nodes, all of these positions here. So it has edges to 8 different objects. And that's how you can represent a grid like a network. Sometimes people cut out these ones and they'll just have the northeast, southwest connections as well. So this is a very different thing, and we'll approach this actually when we come to do a bit of visualization, where we have a look at how you can consider this as a network and what certain properties of a node. For example, if you have a node here, it will only have 5 neighbors and that tells you it must be an edge node. So there's lots of little ways we can treat things that don't necessarily look like a traditional network, but as a network. So let's close that down because the poor computer's struggling with that and OBS. Now, this is a very, very kind of, it's a nice mathematical representation of a network, but it's not very easy for us to read. It's not very intuitive to the human. So what we can do is create something called an adjacency list. And if I just run this, you can see that the output here is a lot clearer. It's basically saying that node A has a connection to B, C, and F. Node B has a connection to A, D, and F. So this connection between A and B and A is actually, it goes in both directions. It's not just one way, it's bidirectional. Now, what are we doing here? Well, we're just taking the network matrix and every row, we're looking along the row, and if we get a 1, we're using this little list up here, this list here, to pull out the letter that corresponds to that connection. And then we're just storing that in a list called connections and printing it out here as network node I, so that would be this bit here, and then all of the connections to that network node. I'm also storing them in something called an adjacency list, and that's what this type of structure, data structure, is called, an adjacency list, because you're looking at all the nodes that are adjacent to a given node. And we can take this adjacency list and we can use network X. Well, you can use any visualization tool you like, but we can visualize it by creating the nodes and then adding the edges to each node. So you can see this code here is clearly commented as to what we're doing. And then all of this here, this is just making it a bit prettier, making it a bit clearer. So if I run that, I can actually talk you through those little changes. So all we have here is the font color I made white because I thought it was a little bit clearer. The node color I made grey, and these two are a bit complicated. Well, not complicated, but there's ambiguity between them. Edge colors with no dash is the circle that goes around the node, whereas underscore color is the actual edge connection here. But I made them both black anyway. And you can see that this is what we would normally expect a network to look like, where we have a bunch of nodes and they're connected to each other. And this is a very, very simple representation. It's sometimes called a graph as well when you're working with networks. And what we're going to do is look at the basics of how we can traverse this. How can you get the computer to start at a position and effectively search this network to find if it's got a path to something, different ways that we can do those searches, and different properties that we can explore for networks. And it's very interesting when you start to look at all the different ways, and this is just a gallery of Network X implementations, often using other tools as well, to show you the many ways you can represent your data in networks. Some of them are very pretty, but we don't just want it to be really pretty, it needs to be really useful and intuitive. You can have made the most beautiful plot, but if it doesn't help you understand your data, it's not useful. And that's really, really important. I did just want to check. Yes, so a lot of the times we'll make use of something called GraphViz or PyGraphViz to help visualize, because Network X isn't primarily for visualization, it's for handling data in the background. But we'll play around with some of that in future videos, and I hope you've enjoyed this very brief introduction to networks. And I think the next video that we're going to explore will be depth first search and breadth first search of a network. So how we get the computer to work its way through a network like this. Thank you so much for watching, and I look forward to seeing you in the next one. Bye!